Okay, so welcome again in this seminar series of topology and geometry. So this is the first series in this semester. So today we have Dr. Sandip Samanta, who did his PhD from IISER Kolkata, and he will give the series of three talks on the group of self-homotopy equivalences. And today he will be talking about some foundation and basic examples for the same. Okay, so over to you.
Yeah, thank you for the introduction. So as told, so I'll talk on group of self-homotopy equivalences. So before going to the exact content of the thing, let me start with like how it's categorically or in generally how these groups appear in categorical sense. So the setup is, suppose we have a category C. So category means it consists of a collection of objects and morphism between any two objects, right? So it's a category, and let's say X is an object in that category. So now we can consider this set, say EQ of X, which consists of maps from X to itself, such that there exists some G also from X to X with F compose G and G compose F, both are identity map on X. So in my category, so this F is a morphism from X to X, and G is also is a morphism from X to X, so that there is a composition rule in the category. It's like in the morphism set, you have the whenever two morphism are composable, they are composable in the like composition rule is there in the category itself. So also the identity map is always there in the uh, morphism sets of same element, right? So if composition of those two things is equal to identity, then we consider the collection of all those morphism in the category, and we denote that by EQ of X. Okay, so naturally this forms a group. So this is a this is a group under composition, right? So if we have two morphism, let's say F1 and F2, then we can compose F1 and F2, because for F1 and F2, you will correspondingly get some G1 and G2, which is kind of in this category, kind of inverse of those F1 and F2. And if I take the G2 compose G1, then it is the corresponding inverse of F1 compose F2, right? So it's a group, and with the identity element being the identity map on X. Okay, so we are now like if we vary our category, then depending on the category, we will get different group this EQX. So for example, if we just standard, if we consider the category to be category of groups, so let's say this and okay, so let's say this is your QX correspondingly. Um, okay, so let's say this is category of groups. Then correspondingly, what will be EQX? So its morphism in the category of groups is the group homomorphism, right? So it's saying that you consider collection of all group homomorphism which are invertible, right? So this is just, if I consider for X, this is just the group of automorphism of corresponding X, right? So this is gives you automorphism group. So similarly, if we consider topological space, where the objects are topological space and the morphism are just continuous map. So topological spaces. Then this saying that each continuous map, there is an inverse continuous map which composed with this thing, which is known to be the homeomorphism group, right? So that gives rise to the homeomorphism group of the particular X that we considered. Oop. We can consider smooth manifolds. So here also the morphisms are basically smooth maps between the spaces. So in this case, the invertibility says that those are diffeomorphism group, right? So maybe in the initial itself, if I just make into like in the category itself, so you can say this way, like this, just morphism from X to X, the C, such that there exists G in the same thing, but in the categorical notation, I'm just writing so that. Okay, so similarly, if we consider Riemann manifold, then the corresponding EQX give you isometric group. Okay. So now in our case, we are specifically interested in this category, not the usual topological space category, instead of this modified topological. So here the object in this category, objects are again topological space only, but the morphism are logical spaces, and morphisms are those are homotopy class of homotopy classes of so topological spaces with also I want the base point as well, or let's say base topological spaces. So base topological spaces means there is a, for each space topological space, you have a choice of base point in that. Okay, and the morphisms are homotopy class of those base point preserving maps, homotopy classes of homotopy class of base point preserving continuous maps. Okay, so this is the category that we are particularly interested in, and we'll see the corresponding group EQX in this category. Okay, so in this category, if we just see what is the EQX, EQX, so it consists of the homotopy class of maps from such that there exists some G from X to X. F is also is a map from X to X, such that this F compose G, the homotopy class of F compose G, and homotopy class of G compose F, those are equal to the homotopy class of identity maps. Okay. So what does that mean? That means that it's basically collection of all maps. So again, there exists this G when I mean there exists G. So there is a canonical choice of definitely base point. So better to write in this form: x comma x0 to x comma x0. X0 is the choice of base point in X. Then so that the composition with F and G, like F compose G and G compose F, both are homotopic to identity map. Okay. So that's the usual notion of homotopy equivalence. So this is basically collection of homotopy class of this is equal to the collection of all homotopy classes of self homotopy equivalences on X, right? So when you say that homotopy equivalence, that means for if F is a homotopy equivalence, then there exists G such that F compose G and G compose F both are homotopic to the identity map. That's what the homotopy. That's why this and it goes to X, so this is self homotopy equivalences. And also like we consider specifically the homotopy class. That's why it's collection of all homotopy classes of self homotopy equivalences on X, right? And this specifically group we are interested, and we will use the notation this script EX for this. Okay. And want to study. So the objective is to study this epsilon X for various X belongs to the object of this category. Okay. So let's start. Why suddenly we are particularly interested in this? So bit of motivation is like see that this epsilon X group, this is already a homotopy invariant. So let me write it as observation. So this epsilon X is a homotopy invariant. So it's homotopy invariant of X. That means like if we have some space X is homotopy equivalent to Y, then these group are isomorphic, right? So we will just pre-compose by the like post-compose by the homotopy equivalence to get the isomorphism. So this Y. So if this X2Y is the homotopy equivalence via F, then you send a homotopy equivalence, let's say G, the class of homotopy equivalence, this G to the, so we want, so F inverse or X to Y, so I have X to Y and I have X to X. So you just compose by F inverse, or let's say maybe the other way. Okay. So F is in this direction, let's say. then I want in this direction. So y to y I have, so g I have, then I have g composite, right? So if start from x, then it goes over y. This is the g. So send this. Okay. So and this will define a isomorphism between these two groups. Okay. So this is a like kind of group which is homotopy invariant in that sense. And also like this but the thing is that this is not functorial, although we have map from this to this whenever there is a homotopy equivalence, but this is not, this is not functorial. So what does that means? That means if we have, if we have some a from x to x, x to y, let's say, then that does not induce a map on the corresponding ex to ey, right? Then that does not induce a map from epsilon x to epsilon y, or in the other way. In neither direction it, like this or this, it does not induce any map, because you can't after composing just by an arbitrary map, you can't guarantee the homotopy equivalence. But this is all still that not bad. Like instead, if we have a functor t, let's say, from our category this th to any, let's say, any category is, let's say this is a functor, is a functor, then we have a map between these things. So uh, then we have a map from epsilon x2. So let's say when I mean by functor, I mean covariant functor. Okay. So the morphism sends in the same direction. So epsilon x2, this is e tx. Tx is the corresponding element in this category C. Okay. So and it's the usual map. And then we have this map, because I can take a ape homotopy class, then you can send this to the T of it, right? Because, and this is again a homotopy equivalence, because the invertibility, right? Like T of ape compose G is T ape compose TG, and the functoriality will say that oh, like after like even after this thing, this is this, and T of identity is identity. So that's why TF is again invertible in this category, and so we have the map. So this is somehow useful in this case, like this, whenever we have a functor, we can get a map in the this group of self-homotopy equivalence. So this specifically for this one, maybe I should write qx. Okay. Okay, so the usefulness of this thing is that in particular we can take various functor. For example, let's say t, we can take to be the homotopy group functor. What is another will be this homotopy group functor Peister. Peister functor. So that sends the this th to the groups, category of groups, and also maybe H star, or like homology functor, or the cohomology functor. All of those sends to this group. So cohomology one is the contravariant. So you have the map in the other way, but still we have the map. And also another thing is that also there is this Postnikov kth Postnikov space functor. So it sends x to its kth Postnikov spaces. So that's another possible invariant that's also again gets mapped to. So these are all same, and this is basically again sends to this sends to again topological spaces. Or we can also have localization functor. So that's again the same, and maybe also reduced suspension functor. So x is sent to its reduced suspension space. So how does that help? Like in this case, we have a sometimes studying the corresponding this image of this T uh, image of this T star, maybe this induced map. Let me write it as T star. Then this T star kind of induce the studying the property of this T star. We somehow sometimes able to say what is the property of this epsilon x might have sometimes. Okay, so this specifically this Postnikov space thing, this is in our case is very important, and many calculation is done using this Postnikov space uh, space decomposition of x. Okay, sorry. Okay, so we'll see the calculation in the next talk. Okay, so somehow it's not properly working. Okay. Okay, so this is very important in our case. Okay, we'll see the specific some example and computation using this Postnikov space functor. Okay, so now let's proceed further to like there's some classical result which already is known. Some literature survey. So the earliest one, earliest one which studied by studies like early in the very early days, the Barkas and Barrett, they first started studying these groups. So this is in they first started in 1958, and for the spaces, suppose X is let's say start with K is a one connected CW complex with cell dimension less than Q, and constructed a space X um, by attaching a Q plus 1 cell to this K. Q plus 1 cell where alpha is a map from the boundary of this cell. So this is SQ to K. Okay. So and for this space, he established a short exact sequence involving the this epsilon X group. Okay. So yes, and there is a exact sequence of three terms. So first I star Q plus 1 of to EX to thing, it's EK if 2 alpha equal to 0 and EK plus E is Q plus 1 if, sorry, this is non-zero if 2 alpha equal to 0. So what is this I star map? This is inclusion map. This I star is the inclusion map of this pi Q plus 1 K to pi Q plus 1 of X induced by the inclusion K to X. Okay. So this short exact sequence he established. So what's the specific use of this exact sequence? See that uh, for some CW complexes, if it is built out of like here the cells of dimension started with a cell CW complex which let's say some finite CW complex we have, and there is a kind of gap, like it has cell up to dimension q minus 1, and then there I'm attaching a cell of q plus 1 dimension, just keeping the q dimension cell all. Then in that case, if I know the original CW complex, the self-homotopy group of the complex K, then we can use, like using this short exact sequence, I can like calculate some, in some cases, this EX for the new space that we construct, like he constructed. Okay. So in that sense, this is a useful result for some specific kind of CW complex. Their finite CW complex, definitely. In that cases, this thing is somehow useful. Okay. So later on, also like in the next time, like next after this one. So this is 1958. After that, many in the
Can you,
19.
hello?
Yes. Yes.
Yeah, so how does this I star pi cube k pi q plus 1 of k gets included in EX? Like it's a map from S cube plus 1 to k, right? So I star
Yeah,
of the homo.
after this is, yeah, so this is so I'm not specified the map. What is the map from I star pi q plus 1 k to this EX? So there is some map so that this composition is 0. So exactly the map I didn't specify. So there is some map here. So this
Okay.
group, this I star of this thing, so it is a like subgroup of this pi q plus 1 of X. So that is somehow there is a map there. So it's also not saying anything about injectivity or anything. Okay, it's just a like after this compose, that thing is 0. That's why just three terms sort exact sequence, not even saying that this is injective or something. but still in some cases that might help in computation. Okay, so later on in after 58, next works come almost after 6 years in 1964. Like many authors starting these things. So like the first pioneer is Khan, then C, and mostly the Argovich Kurzweil. So they all in 1964 all started studying this group EX, and they also mostly use this Postnikov decomposition. So they mostly use the Postnikov decomposition. Composition of spaces to get various exact sequence, and started saying like in specific case what could be the group this EX. Okay. Sequences. So we'll in the next talk we'll see specifically how this Postnikov decomposition is done. So I'm just saying for the timing there is this decomposition which is important in saying like this decomposition is somehow giving a step-by-step inductive process to get the information about this X, this EX. Okay. So later on also work of this Nora and May. So later on also have 66 million. Kudo and Tushita Carter. There in this is Nora. This is in 1967. It's 1988. And so on. They all studied these things in various contexts. So in particularly like there are other kind of variation of these self-homotopy equivalence groups. So in the EX we started with the like homotopy equivalent self-homotopy equivalence which preserves the base point, so one can study the free version of it as well, and there is study of that thing as well. And also if the space X instead of just topological space, if there are extra structure like there is a multiplication which is called H space structure, if they have H space structure in some cases, that cases we specifically want instead of just homotopy equivalence, we restrict to self-homotopy equivalence which are also H map. Then in that cases what's the structure of these groups, they like all of those things are studied in different contexts. Okay. So in so the next kind of another observation or property that these things has some basic properties. Like just to get the feel what kind of this EX are. So see that if we have any finite group, then any finite group can be realized as a subgroup of these groups. So the first thing is that any finite group can be realized as a subgroup of some subgroup of ex for some x for x for some x. We can assume this is some x. Okay, some x. Let's say. So how can we do that? So note that suppose we start with a group G, which is finite finite group, and its cardinality, let's say, let G equal to n, right? Then G acts on itself, like the uh, acting G on itself by left multiplication or right multiplication. Those are a group homomorphism inside this thing. So using that, we can see that G sits inside the group of symmetric group with n elements, right? So we can assume like see G as a subgroup of the symmetric group with n letters. Symmetric group. Right now, if we can see this Sn as a subgroup of this Ex, because these are kind of on product space. This canonically acts on the product by permuting the factors of on the product, right? So let's take a space Y, which is let's say non-contractible. Non-contractible. And form X as Y cross Y n times. Then on this X, Sn acts naturally by permuting the factors. And so that means we have a map from Sn to and the permuting the factor is again a homeomorphism basically, right? Because if we permute a factor, the corresponding sigma inverse does the reverse thing, and it will give the identity map. So it's basically sigma n is sits inside homeomorphism group of X, right? Just by the action itself. Now, if we mod out by the if we mod out by the homotopy, still it's giving us injective map, right? Because we assume our X be non-contracted. So that's the permuting the factors of X is no, it's non. Or maybe just it's a homeomorphism first of all. So that means if I using the previous thing, if we have an element sigma, Sn to X, if we have a sigma, we correspondingly we have the permutation action, and correspondingly we consider the, let's say, I say f sigma to be the corresponding element which permutes the factor via. So f sigma is from x to x. So here I have x1 through xn. It's just sent to x sigma 1 through x sigma n to this map. So I can send it to the corresponding homotopy class of F sigma. And this is a homomorphism. So in particular, it lands in the correct space. Like it is also included inside the EX. So I'm saying that this is also injective. This is still this is still injective, because if not, so that means injective means if sigma is non-identity permutation, then the corresponding uh, F sigma, the class of this thing, is not the homotopy class of identity maps on X. And that is even like one can easily get the contradiction. Like if this is identity, let's say if F sigma is homotopic to, so equal to identity, that means F sigma is homotopic to the identity map. F sigma is homotopic to the identity map on X. So there exists some G again from X to X such that F sigma compose G is identity, and or let's say uh, GT, I specifically mean GT, such that G0 is F sigma and G, just the standard definition of the homotopy identity X. And as sigma is non-identity, so I can take, so there exists some k comma L such that sigma k is sigma k equal to L with k not equal to L. Okay, because it's not identity, so there exists some point which is not fixed by sigma. So in particular, this is the pair k and L with k not equal to L. Okay, then I can take from this thing, I can define a homotopy from y to y. So basically, what I'm trying to, if this is not identity, then I'll say that this y, which I started with, that I assume to be non-contractible, I'll show that is actually contractible. And that's almost immediate from this thing, that you define the map a, let's say HT from y to y. How you define? So you go from y to this y cross y cross y, that means to x n copies. So this is my x. And here you apply your GT, and then again you go to y cross y cross y, and from here you go to x here. So this map is known. Now I want somehow at the 0th level, it should be at the 0th level, I want to show that this is F sigma, not F sigma. So to show the contractible, so identity map should be homotopic to the constant map, right? So at the H0 level, it should be some identity map. At the H1 level, it is like constant map or the other way. So you include this y factor to the space, like to the point at the kth place, right? So you just send the first y that to here at the y at the kth place, and remaining places are the y0, which is the base point we started with. All the remaining places are y0. Okay, then under GT map at the 0th level, X sigma does the permutation to send it to like the kth place. Kth place will go to the lth place here. So now under GT map at the 0th level, so it goes to the lth place here, and then I can project this projection onto the lth coordinate. If I do, then at the 0th level, I'll get the identity map. and at the 1th level, this GT being identity map. So at the this y still in the kth place, and when projected to the Lth place, I get the y0 because k is not equal to L. So this map is specifically says that this H0 is identity map on y, and H1 is the constant map y0. So that means I have this y is contractible, which is a contradiction. So this map is still an injective map, and we have like this Sn is still sits inside this group Ex. Right, so we can like see all the symmetric group sits inside this group Ex for X some non-contractible. Just non-contractibility is enough. We can assume anything simply connected CW complex, whatever good assumption on X we need. Okay. So so in that sense, like these Ex groups are kind of does not inherit something that finite groups has some property, like so some group theoretic property, like those things does not inherit into the Ex group. So those are kind of something bit wild in that sense for spaces. So various different type of spaces X. So but that's that's specifically those things. But in some special cases, we can directly compute the this group Ex, and just using some basic topology. Okay, so one such example, let's see this example. Okay. Okay, so the first example may one start with. So examples or let's say basic computation. So just so the previous thing is clear, right? So is there any confusion here? Okay, so then we go to the example here. So saying so, what would be the E of Sn? So let's compute this. So so if is a if is an element here Sn, then this specifically one representative of this class, let's say F is the thing. So this Sn to Sn map that induce a map in the homology group. So Hn that induce Hn Sn to Hn Sn, and this is isomorphic to the integer. So I'm considering the homology group with respect to the coefficient z only. Whenever I'm ignoring the coefficient, it means with respect to the z coefficient only. Okay, then so f star being an homomorphism from z to z, so that is determined by an integer, right? So for each f, the corresponding f star is determined by an integer. So that's called the degree of so this is determined by some integer, let's say multiplication by some t. So this degree of f, that is that map T which determines this f star map, right?
Sorry, sorry.
But I can't remove that. Can you remove that thing? I could not. Sorry, thank you. Okay, so on degree of f, this is the D, and this exactly determines all the morphism from Sn to Sn. So in the homotopy class, so F is homotopic to G if and only if degree of this degree precisely determines the homotopy homotopy classes for that thing. So this, so degree G. So one direction is immediate. If F and G are homotopic, then the corresponding F star and G star are same map, so the degree is same. But for the converse part, one needs the what's called the Hop degree theorem to get the if the degree is same, then to construct a homotopy between those two maps, one need the Hop degree theorem. So in that sense, the EX, so when I'm considering F in EX, then that's a homotopy equivalence. So F star map is not just any arbitrary map, that is an invertible map also, because G star will induce the thing. Now, if we have F star in Z to Z, then the only invertible map, like I have also the identity map. So the degree thing also have the property that it's multiplicative with that thing. So this is 1, this degree is multiplicative, that means degree of F compose G, that is degree of F times degree of G. That is again easy to verify, because F star F compose G whole star is F star compose G star, and then the this thing follows. So, and also the identity map induces degree of identity map is 1, because identity map induces identity map on the homology. So identity Sn, so that's 1. Now use these two things to get that if F is a homotopy equivalence, if F is a homotopy equivalence, then degree of F is only possible is plus minus 1, because for F there is just a G such that F compose G is homotopic to identity. If we apply the degree on the both side, then it says the degree of F compose G is equal to the degree of the identity map, which is 1. So degree of F times degree of G, that is 1, but degree of F G both are integers, so multiplication of two integer is 1. That means the only possible choice for F is plus minus 1, right? Then degree of F equal to plus or minus 1. And once this is done, then the only possible F that correspond to this degree is plus minus 1. That implies that this E of Sn, this is isomorphic to the set plus minus 1, which is same as just J2, right? So for Sn, we have the this group of self-homotopy equivalents that is isomorphic to Z2. Just using the degree thing, we didn't have to worry about anything specific to n or something. Similarly, another example that we can compute using little bit of this topology information is the group of self-homotopy equivalents on. Okay, so let me try it as on the Eilenberg-MacLane spaces. Okay, so B, this is E of KGN. So this, what are these KGN spaces? KGN are the Eilenberg-MacLane spaces. So these are the topological spaces of CW type, and such that the only homotopy, they are specified by the homotopy groups. So the only non-zero homotopy groups of let's see, groups of these spaces are concentrated at like at the nth degree. So KG, and this is isomorphic to G if P equal to N or 0 otherwise. So remember that in this case, if n is equal to 1, then I need to, like, I can have G to be anything, but for like G is any group. And if n is greater or equal to 2, then I need to have the G to be some abelian group, because the higher homotopy groups are abelian, and in this case it is isomorphic to that thing. So G has to be abelian in those cases. But for these cases also, we can compute this EKGN. So here I want to have like, if we have a map from KGN to KGN, then they're using the like this classical result. So recall that there is a correspondence between the homotopy class of maps from these Eilenberg-Maclaurin spaces and the cohomology group. So it says that this, if I have a space X and KGN, so this bracket means the this consists of all homotopy class of continuous maps, no base point preserving, just the continuous homotopy, like continuous homotopy class of maps. These and the nth cohomology group of X with coefficients in G. Okay, so using these things, so even if we have a base point preserving map, but that I can also assume that just as a map homotopy class of maps from KGN to KGN. So take X to be your KGN itself. Then it says that this F, the homotopy class of this F, is correspond to some element in the nth homology, like some alpha, let's say. Some alpha belongs to the nth cohomology group of this KGN with coefficients in G only. Okay. Now using this information on the homotopy groups, I can see that these KGN spaces are n-1 connected, right? Till the until it reaches to n, all the lower homotopy groups are 0. So KGN spaces are n-1 connected, and for such things, these cohomology groups are isomorphic to the homomorphism from the HN KGN to G. So the homology group, these correspondence, this is again by universal coefficient theorem. Using the universal coefficient theorem, one can see the cohomology group as the Hom. So Hom, this means like as Z module. So homomorphism from HN KGN to G. Okay. And again, as these KGNs are n-1 connected, so Hurewicz theorem says that Hn of KGN is isomorphic to pi n of KGN, and pi n of KGN is isomorphic to G. So that says that this is ultimately Hom of G to G. Okay, so this is by Hurewicz. Hurewicz theorem. Okay, and yes, so this is by Hurewicz theorem. So ultimately, for if we start with a homotopy equivalence, so we didn't start with any homotopy equivalence. Just if we assume a map from KGN to KGN, then its corresponding homotopy class correspond to an element of the homomorphism from G to G. Right now, if we impose the condition that F is a homotopy equivalence, then what happens if F is a homotopy equivalence? Then for this F, there is also a inverse of this thing. G is also there, right? So this correspondence being an homomorphism. So that says that this on the right hand side the homomorphism is also invertible. That means this is a correspond to a element of the automorphism group of G. Homotopy equivalence. Then if the homotopy class of this correspond to the an element, let's say if tilde in the automorphism group of G. And conversely also, because this is a one-on correspondence on the previous level itself. If I have a automorphism, then on the right left hand side it also induce a homotopy equivalence. It has to induce a homotopy equivalence. So from this point we can say that this is the group, this is isomorphic to the automorphism group of G. Okay, so for these two spaces at least we have calculated the these EX groups, and they are using the basic topological tools. We can get this easy calculation, and they are very much familiar groups to study. For the other spaces, when we complicate the spaces, this X where we have more non-zero homotopy groups. So this is in the homotopy level, it is very like these Eilenberg-Maclaurin spaces are quite easy to understand. There is only one homotopy groups at the nth place, and everything is zero. So people have studied spaces which has very like finitely many non-zero homotopy groups, or finite CW complex. For those spaces, how these groups EX will look like. For those things, they have said that whether those are finitely generated or finitely presented, or sometimes nilpotent or solvable. All those things are studied for specific restriction on the space X. So we'll see some of those things and some other example of the spaces where you can like we'll use this various method of Postnikov tower decomposition, or some mapping cone construction to calculate some other spaces in the next thing. So I'll stop here for today, and for the other for the other variant of these things and some subgroups, natural subgroups of this EX, those will also will come up in the next talk. So so I'll stop here. So if there any question, please unmute and please say.
This last thing you said, right? That
Yeah.
E of KGN is odd G. It's just morphism from G to G, right? Abelian group morphism. It will not be odd, right?
No, like
The G morphism will give me a map from HKGN to G.
no, in
Yeah.
the epsilon KGN, it consists of homotopy equivalents. So if I start with just a map, then it's correspond to homomorphism from G to G. But if is a homotopy equivalence, then the corresponding on the right hand side, it also be a like isomorphism of groups, right?
Oh, okay, I get it. You can compose it and get
Yes.
identity, and you can do that there as well. Okay.
Yes. So that's why it gives us in just at
Yeah,
the space level map, it gives correspond to
yeah.
homomorphism G to G.
If just we want the homotopy class of maps, then you
Yes.
consider the morphisms. Okay.
Yes, exactly. Right. Any other
Okay.
question?
Yes. Yes, no. Then let's thanks to the speaker, and we'll meet again on next Tuesday at the same time. Okay. By then, bye.